Alright, so next let's talk about how can we do a sample of the subgraph from the input graph dataset for the representation learning. So the sampling algorithm we use in the Graph-Bert actually is based on the PageRank algorithm. We try to use PageRank to measure the similarity or closeness among nodes in the graph. I hope you have heard about the PageRank algorithm, right? If you know, the Google component is built based on PageRank algorithm actually for their first version of the search engines. So the PageRank try to provide the ranking of the web pages on the internet. Then in this way, if we have some such keywords, then we can have the corresponding ranking of different web pages containing these keywords, right? So the high-level idea for the PageRank is to provide a ranking for different web pages on the internet. At the same time, if we think this web page as a node and the connection or the hyperlink among the web pages at the edges, we can define this internet as a graph as well, right? So in this page, we'll show you with a toy example to illustrate how can we learn the ranking scores of the web pages on the internet based on the toy graph. Let's assume if we have an internet, we have 5 different web pages, 0, 1, 2, 3, 4, and so forth, right? And among these web pages, we also have some connection of hyperlinks, for example. Then if we have one hyperlink from web page 0 to web page 1, then we can add one link directing from 0 to 1 as shown here, right? And so forth, similar for other edges. Then in this way, we can define this internet as a direct graph as shown here, right? With only 5 nodes and also extensive connection among the web pages, among the nodes. So on the internet, when we're browsing one web page, we can either following the hyperlinks on this page to jump into some other pages. At the same time, we can also jump to some pages, maybe not directly connect to the current page randomly instead, right? Therefore, to modeling such kinds of factors, we have one term which is called alpha as shown here to measure the probability for the user to jump to some other random pages on the web. So we define the alpha as the probability for the user to jump to any pages on the web with the equal probability. At the same time, if the user chooses to stay based on the current page and also follow the hyperlinks to some other pages, then we can define this probability as 1 minus alpha as shown here, right? It measures the probability for the user to click the links in the current page to go to some other pages. So let's try to model the way we browsing the web pages. This kind of factor can be very important. Generally, we have to tune this alpha very carefully so we can model the way the user will be browsing the web pages on the internet. Okay, so we have this graph. We also have this alpha, this factor that we define here. Then we can show how can work with the PageRank algorithm. So given the input graph as something like this, we have 5 different nodes. We also have some connection among them denoting the hyperlinks among the web pages, right? So we can borrow the connection among the nodes in the graph as a matrix, as a adjacent matrix, like A as shown here. So we know that this web page 0 is connected to one single node, 1 as shown here. So to borrow in this connection, we can have one entry, from 0 node to 1 node with value 1, denoting they have one connection, right? Since this node 0 is only connected to one single node with one outer link, right? Therefore, for the first row in the matrix, we only have one single entry filled with value 1, and all the remaining are zeros. And when it comes to the web page 0 or node 0, it has 5 different outer links connecting to some other nodes, right? Now we have 2 coming to the node 2, we have 2 coming to node 3, and we have 1 coming to node 4 as shown here, right? Therefore, for the second 0 and corresponding to the node 1, it will have 2 edges connected to the node 2, 2 edges to node 3, and 1 edge to node 4 as shown here, right? And so forth. So we can describe the connection among the nodes with this adjacent matrix A as we define here. It measures the link counts among different nodes. So we can read the values in the matrix by rows. This one denoting the current node, right? And this column denoting the next node we will go to by the edges. Now, if we are going to one single node, the node 3 as we show here, we know that this node 3 will have one edge coming to node 0, right? As we show here, right? According to the matrix, and so forth. So besides the adjacent matrix we define here, we can also measure the degree of the nodes. Since the edges in the graph they are directed, therefore we will have 2 degrees, covering both the outer degree as well as the in degree of the nodes. What is the outer degree? Outer degree measures how many edges are coming out from the nodes. The in degree will measure the number of links coming into the nodes instead, right? So we care about the outer degree of the nodes instead here. We measure the degree by this vector, right? So the node 0 will have one single edge coming out, therefore its degree is 1. And for node 1, it will have 5 edges coming out, therefore its outer degree will be 5 instead, and so forth. So in the page ranking algorithm, we try to model the way people browsing the web pages, and we try to model the way they were jumping across different web pages, right? Therefore, according to this factor, alpha, together with the connection among the nodes, we try to define its corresponding transition matrix among the web pages. We know that the transition matrix will cover two factors. One is transition among the pages, by the user following these edges, by following the hyperlinks, for example, right? So besides the transition by following the hyperlinks, we also have some transition by some random jumping, right, as denoted by this alpha factor as shown here. So therefore, for the define the transition matrix among the pages, we need to have two factors. The first part is for the leaping or jumping probability distribution among pages, which is purely defined by the alpha term. And we also have this 1 minus alpha times this A matrix. So when we measure the transition probability among the nodes in the graph, we have to normalize the values we have in the adjacent matrix by the degrees. So instead of using the number directly, we have to normalize all the numbers by dividing them with their degrees instead. So the way we do the normalization is by dividing each row by its degree, in the matrix A. So for example, for the first one, it has one single entry with value 1, its degree is also 1, so we divide this one by the 1 we define here, right? Then for the second row, we will have two entries with value 2, one entry with value 1, its degree is 5. We can divide this 2 and 1 by 5. Then this one will be corresponding to 0.4, 0.4, and 0.2 instead, right? And so forth for the other rows in the matrix by dividing by the degree of the nodes. And we can further times a normalization version of the A matrix with the 1 minus alpha as we defined before. So by adding the probability distribution among pages, following this kind of links as well as the jumping probability distribution, we can define the final transition matrix G by summing them together, right? This is one way to define the transition matrix among different nodes in the graph. Then how can we use this matrix G for measure the ranking scores of the nodes in the graph, for the web pages? So we know that by following either the connection among the nodes or by doing the random jumping, we can jump across different nodes, right? Then in this page, we try to consider to use this kind of mechanism for measure ranking scores for all the nodes in the graph. And we can define one initial ranking score for all the nodes as a v-vector, right? So we don't know what are the ranking scores should be, and we can assign them with equal values. They have the equal ranking scores initially. Then we can do the updating of the ranking score for all the nodes iteratively in the page ranking algorithm. If we don't consider the jumping across different pages, do the random jumping, and we just follow the connection among them, we can do the updating of the ranking scores by times this v-vector with the A matrix, right? So if we times this A with a V, it denotes that. And if we times this A matrix with a V vector, it measures the distribution after we do the jumping with one step, from the initial distribution, right? If we further times this AV with the A matrix again, A square V, it measures the distribution if we jump with 2 steps. What are the ranking scope for us to add different pages, right? And so forth. We do the updating with multiple steps until we can achieve convergence. If we have some 2 jumping, like A7, this is raised to 7 as the power times V, and A raised to 8 power times V, and we find that they have the same distribution, right? Then we can say that we can achieve convergence for calculating the ranking score among different pages. And this vector can be returned as a final page ranking scores for different pages in the graph. So here we just following the connection among the nodes. We don't consider random jumping, right? If we further incorporate the random jumping into the calculation process, then we can update the V vector iteratively by the formula we show here instead. So we know that we have one initial ranking score, which is V0, we define like this one, right? And we can updating this ranking score, iteratively by following the formula we show here. We can either following this connection among the nodes. We time this vector V with this A matrix, denoting the transition among different pages, right? At the same time, we also have some random jumping across different pages as well. Therefore, with the factor will be 1 minus alpha times A bar times V tau plus with alpha times V0, right? This denotes the random jumping following the initial distribution, right? And this one measures the probability distribution by jumping across different pages following this connection among the nodes. It's A bar denoting the normalization version of the A matrix we defined before. And then we can do the iterative updating of the ranking score for all the nodes in the graph by following this formula until convergence. What do we mean by until convergence? If we have see that this V tau plus 1 equal to this V tau, then we can say we have achieved convergence already. Then we can have a very interesting observation, because if we can achieve convergence, in other words, this V2 will be equal to V2 plus 1. And we can replace this V2 with V2 plus 1. Then we can actually have one solution for the V2 plus 1. It equals to what? It will be equal to S matrix times with the V0. In other words, instead of doing this iterative updating of the vector V vector we show here, we can actually calculate this V vector directly by following the formula that we show at the bottom part. We define this V2 plus 1 at convergence as equals to the S matrix times V0. This V0 is the initial, ranking score among different pages. These are normally assigned with equal values. And we can calculate the V2 plus 1, the convergence 1, by times this V0 with one S matrix. And what is this S matrix? This S matrix equals to what? Equals to alpha times, we have the inverse of this matrix. Inside it, we have the I matrix denoting this identity matrix minus 1 minus alpha times with the A bar as we show here. Therefore, by using the S matrix we define here, we can calculate the ranking scores among different pages directly based on their S matrix as well as the initial distribution of the ranking scores V0. And it can save lots of time for calculating scores among different ranking scores among different nodes in the graph. So let's come back to the sampling part. How can we sample the subgraphs in the input graph for the representation learning? So we do a sampling also based on the page rank scores among different nodes. So we mentioned before, we can define one matrix S for calculating the convergence of ranking scores among different nodes. Actually, this S matrix also measures the closeness among different nodes in the graph. In other words, given an input graph, we can define its corresponding matrix S for measure how close other nodes are in the input graph. Then based on this S matrix, we can further do the sampling of the subgraphs. And how can we do the sampling? So for each of the nodes we have in the either training set or testing set, we can sample one subgraph for it as a target node. Now here, if we use this VI as a target node, we plan to learn its embedding vectors or representations. We use this VI as a target node. At the same time, we will sample a set of neighbors from it. And we sample the neighbors according to their scores we calculated in the intimacy matrix. And how can we do the sampling? Let's assume if this VI is the first node in the graph and corresponding to the first row in the matrix S, then according to this row in the matrix, we know which nodes are closer to the target node, right? According to the values. So therefore, according to this S matrix, so we pick a row according to the V node in the matrix, and this row we measure the closest scores among all the nodes in the graph to the node VI, actually, right? Therefore, we can pick the top k nodes with the highest closest scores to the node VI and summarize them out. So for the target node together with the sample top k neighborhood nodes, we can define them together as a node set for a subgraph. Because here in the following part, we don't need to have the edges among nodes, therefore we have an empty set for the edges for the subgraph. We can define this one as a subgraph sample for the VI as a target node. Besides the node VI, we can do a sampling for all the nodes in the graph as well if we plan to learn their embedding vectors.